All right. Good afternoon to everyone. For today, we'll be discussing our second module following our curriculum given from CHED. We'll be talking about this time about operational amplifiers. So by definition, an operational amplifier, often abbreviated as op-amp, is a versatile and widely used electronic component designed to amplify voltage signals. It's a key building block in many electronic circuits due to its high gain, high input impedance, low output impedance, and versatile applications. So in terms of amplify voltage signals, it refers to the capability of an op-amp to increase the amplitude of an input voltage signal. The primary purpose of an op-amp is to amplify the voltage difference between its two input terminals and provide an amplified output signal. In summary, an ideal op-amp for voltage signal amplification would have high gain to provide significant amplification, high input impedance to avoid loading the input signal source, and low output impedance to drive external loads effectively. These characteristics make op-amps versatile and suitable for various applications in electronics such as in signal conditioning, audio amplification, and instrumentation circuits. So in terms of the symbol and terminals, the op-amp symbol in circuit diagrams provides a simplified representation of the op-amp's functionality and characteristics. It helps engineers and designers quickly understand the role of the op-amp in a circuit without delving into the internal details. The symbol typically consists of a triangle which represents the amplifier with two input terminals, inverting and non-inverting, and one output terminal. The orientation of the triangle indicates the input and output polarity relationships. In terms of the terminals of an op-amp symbol represent the physical connections to the external circuit. These terminals define how the op-amp should be connected within the circuit for proper operation. In terms of the differential inputs, inverting terminal connected to the inverting input of the op-amp. The inverting input is where the inverted version of the input signal is applied. The op-amp amplifies the voltage difference between the inverting and non-inverting inputs. Non-inverting terminal connected to the non-inverting input of the op-amp is where the non-inverted version of the input signal is applied. The op-amp compares this input with the inverted input. Output terminal out represents the output of the op-amp where the amplified signal is obtained. The amplified output signal is obtained from this terminal. Power supply terminals plus V and minus V provide the power supply voltage to the op-amp. Positive and negative voltage supplies are typically required for proper operation. The power supply terminals provide the necessary voltage to operate the op-amp. Offset null or offset adjust if present is used for adjusting the DC offset voltage in certain op-amp models. High input impedance means that the op-amp presents a minimal load to the connected input signal source. In terms of the function, high input impedance prevents the op-amp from drawing significant current from the source, ensuring that the signal source is not significantly loaded or affected by the op-amp. High gain in an op-amp means that the device can significantly increase the magnitude of the input voltage. A high gain allows the op-amp to provide substantial amplification, making it suitable for applications where a small input voltage needs to be magnified to a larger output voltage. Low output impedance means that the op-amp can drive external loads with minimal voltage drop. Low output impedance is essential for maintaining the integrity of the amplified signal when it is connected to subsequent stages or loads. It allows the op-amp to provide a strong, stable output voltage even when connected to varying loads. In terms of the purpose of the open loop configuration, it is primarily used for applications where very high voltage gain is required, and the precise control of the output is not critical. Open loop amplifiers have a large amplification factor, but they lack stability and accuracy. In an open loop configuration, number one, the feedback path is open, meaning there is no feedback network. Number two, the output of the op-amp is solely based on the difference in voltage between the inverting and non-inverting terminals multiplied by the open loop gain of the op-amp. And number three, open loop configurations are not commonly used in practical applications because they are highly sensitive to component tolerances and changes in temperature, making them unreliable for most purposes. As per the closed-loop configuration, it is designed to provide stability, precision, and control over the amplifier's characteristics. It is widely used in practical applications where the output needs to be well-defined and stable. In a closed-loop configuration, number one, the feedback path is closed, meaning there is a feedback network that connects the output back to the one of the input terminals, either inverting or non-inverting. Number two, the closed-loop configuration introduces negative feedback, which stabilizes the op-amp's performance and reduces sensitivity to component variations. Number three, the closed loop gain is determined by the feedback network and is generally much lower than the open loop gain of the op-amp. And number four, closed loop configurations are commonly classified into different types such as inverting amplifier, non-inverting amplifier, differential amplifier, and integrator, each serving specific purposes based on the desired signal processing characteristics. In terms of the advantages of closed-loop configurations, number one, improve stability and reliability. Number two, reduce sensitivity to component variations. And number three, precise control over the gain and other characteristics. In summary, open-loop configurations provide high gain but lack stability and control, making them impractical for most applications. Closed-loop configurations, on the other hand, offer stability, precision, and control by incorporating negative feedback, making them suitable for a wide range of electronic applications. The common mode rejection ratio, or CMRR, reject common mode signals or signals that are the same on both inputs and amplify only the differential signal. The primary purpose of CMRR is to quantify the amplifier's ability to reject common mode noise or interference that may be present in the system. Common mode signals are often undesirable and can be caused by external electromagnetic interference, power supply noise, or other sources. CMRR is crucial in applications where the accuracy and fidelity of the differential signal are essential. In instrumentation and communication systems, a high CMRR is desirable to ensure that the amplifier responds predominantly to the differential input signal and minimally to common mode disturbances. As per the practical considerations, real-world amplifiers cannot achieve infinite CMRR, but a higher CMRR value indicates better common mode rejection. CMRR is affected by imperfections in the amplifier circuit, such as component mismatches, imperfections in the differential amplifier stage, and limitations in the op-amp's characteristics. In summary, the common mode rejection ratio is a crucial parameter for amplifiers in applications where common mode noise rejection is essential. A higher CMRR value indicates better performance in rejecting unwanted common mode signals, contributing to improved signal fidelity and accuracy in differential amplification applications. These are the applications of the operational amplifiers. Basically, operational amplifiers find applications in a wide range of electronic circuits, including amplifiers, filters, oscillators, voltage regulators, and more. They are a fundamental component in analog electronics and are often used to perform mathematical operations such as addition, subtraction, integration, and differentiation. Power supplies. Op-amps typically require dual power supplies, positive and negative voltage, to operate. However, single supply op-amps that operate with only a positive voltage supply are also available. In summary, an operational amplifier is a versatile electronic component that amplifies voltage differences between its inputs. With high gain, high input impedance, and various configurations, op-amps are essential for a wide range of applications in electronic circuits, making them a cornerstone of analog electronics. So I think that's it for the discussion of the operational